Okay, so last time we already discussed about the Martensite in steel, the transformation of Martensite from austenite, which is related to the carbon content. Okay, so in steel with under 0.2 weight% of carbon, okay, and trenches causes the FCC austenite transfers into BCC Martensite. And in higher carbon steel, the austenite transfers into a BCT martensite. It's a body center tetragonal structure. Okay, so if we look at the microscope, we see some needle shape, okay, or some spike under the microscope, because this transformation, Martensite transformation, is dimension as diffusionless. Okay, it's diffusionless. Okay, so the figure A shows the just the low carbon steel. Okay, and the figure B presents the high carbon steel. It's a kind of the plate martensite. Okay, plate martensite. Okay, so the martensitic reaction and tempering. As I already mentioned previously, that the so this change process will trigger this Martensite transformation, right? And the hardness and some mechanical properties of Martensite are, are really much stronger than other steel with the some specific carbon content, right? And if they already if this martensite already formed, however, its mechanical strengths or such as the UTS or the hardness are stronger than what it wants. And how can we reduce its mechanical properties? Okay, and this approach is called tempering. Okay, it's a tempering. Okay, okay. If we temper this martensite, its tensile stress, UTS, the unit stress, and the hardness will reduce dramatically. In this figure shows if we temper the martensite at say 400 Celsius, and its UTS would drop substantially, and its unit stress would drop, and its hardness decays, right? With increasing temperature, increasing the tempering temperature. Okay. Okay, so we can summarize that the Martensite formation, okay, start from austenite, right? Austenite FCC structure. If the slow rate, if the cooling rate is slow, and the transformation will form the ferrite and the cementite, right? And if the cooling rate is fast, that means the trench process and martensite will form. Okay, if we want to reduce the mechanical properties, reduce the ultimate tensile stress or the hardness or the unit stress, and we just do the tempering. Okay, and this martensite will transfer into ferrite and cementite. Okay, cementite. And due to this dimensionless transformation, the BCT, the body center tetragonal, with the initial concentration higher than 0.15 weight% of carbon, that the causes fuel slip plan. Okay, okay, because this transformation is dimensionless, it is time independent. Okay, and the grain grows very fast. Okay, Therefore, this it's sleep plan a few than other structure. Therefore, its mechanical properties are brittle and hot. Okay. So let's control the eutectoid reaction. This is the TTT diagram, right? So this figure just tells us if you need a high hardness martensite, or you want to control the hardness. So what's the uh, controlling parameters that you have to adjust? For example, I want to get a higher hardness, so the Rockwell hardness is about like 66. So what's the parameter you should control? So delta T, right? I already mentioned before. Delta T is the driving force to control the eutectoid reaction. Okay, and you can modify the delta T to get the specific mechanical property, such as the hardness that you want. Okay. Okay, so what is delta T? Delta T is the TE minus T, right? For example, I want to get the hardness, the Rockwell hardness about 66. What's the delta T should be? What's the T? What's the temperature? What this T should be? Say maybe it should be right here, right? Right here. Therefore, its delta T is from the eutectic, right? Temperature to say like maybe 50 Celsius, and this is delta T. Okay, if I just wanted the Rockwell hardness about like 40, okay, 40. So the delta T is in the range to here. All right, you get what I'm saying? You get what I'm saying? Like for here, this delta T is about like 700 something, and for this delta T is about 200 something, right? So if we want to control the mechanical properties such as hardness, the delta T is the driving force. Okay, it's the driving force. Okay, so the effect of adding other elements changes transition temperature. So if we add other elements such as chromium, nickel, molybdenum, silicon, magnesium, and those adding or those alloying elements can retard this austenite transfer into alpha and the cementite. Okay, so for some transformation with alloying elements is able to retarding this reaction, this eutectoid reaction. Okay, so if you can compare with this figure with the previous one, okay, with the previous one, this is alloy, this is alloy, okay, this is alloy. In this figure is alloy. It's a steel 4000 4340 4340. So this is alloy, right? It's alloy. Okay, with some alloy elements. So we can compare with the this for example, this is our TE eutectoid temperature right here, right? Right, and this is austenite gamma solid solution, right? And at this point, for example, we have isothermal temperature drop to like here, and we keep the temperature with a constant. Okay, and this austenite will start transfer to ferrite at this time. Okay, and finish at this time. and start to form the perlite at this time, and finish to form the perlite at this time. Okay, you get what I'm saying? Okay, so we can compare this figure. So if I have the same delta T with this figure, that means say this is 650, right? So if I has this temperature 650 right here, draw a line here. It's isothermal. That means the temperature is a constant and remaining for longer time. So for here, this is the austenite, right? And at this point, the perlite starts to form, right? And at this point, already completely transferred into perlite. Okay, so what's this time for perlite start to form? Oops. Time for perlite start to form. Well, it's about a few seconds, right? It's about a few seconds. The perlite starts to form. So how about this figure? The perlite start to form where? At this moment, right? You know what I'm saying? At this moment, the perlite start to form. However, for this figure shows that the perlite start to form a few seconds. Okay, a few seconds. Okay, so for this transformation diagram, it's only iron and carbon system, right? And for this one is alloy system. Okay, iron, carbon with other alloy elements. Okay, and those alloy elements are able to retard this transformation, phase transformation. Okay. Okay, so let's consider a real case that the continuous cooling transformation. So previously we discussed this isothermal transformation. So that means the temperature remained constant for a longer time, right? That means we drop the temperature. We have the delta T, right? So we drop to the transformation temperature and keep the temperature at the constant or fix the temperature for a longer time, right? However, in the real case, the isothermal heat treatments are not the most practical to conduct because an alloy must be rapidly cooled to and maintain at an elevated temperature from the higher temperature above the eutectoid. Right? We cannot wait. We need to produce this alloy. Therefore, the cooling rate should be rapid. Okay, and the isothermal transformation diagram is only valid for the conditions of constant temperature. Okay, and this diagram must be modified for transformations that occurs as the temperature is constantly changing. Therefore, for continuous cooling, the time required for a reaction to begin and end is the light. Okay, so this is important. You have to remember that for continuous cooling, the time required for a reaction to begin and end is the light. Okay, so we have to we have to consider a real case. That's mean the continuous cooling. Continuous cooling. Let's look at this figure. We already know this, right? This is a TTT diagram. So for isothermal treatment, that means we drop a temperature. We drop the delta to a certain temperature, right? For example, I drop to 600 Celsius, and I remained this temperature is remaining for a longer time. And we know it's eutectic start to form at this point, right? And in this phase completely transferred to pearlite at this point. It's dotted line. Okay. However, in the real case, the cooling rate is rapid. Okay. Okay. So this blue line shows the real cooling, continuous cooling. Okay. So the temperatures keep reducing, right? It's keep reducing. Okay. So what's this line tell us? What's this curve tell us? Okay. So for the real cooling rate, for the continuous cooling, okay, the transformation will delight. So this dot line means the isothermal. Okay, and so this line is continuous cooling. Okay, continuous cooling. Okay, so for, oh, sorry, I have to adjust it a little bit. It's wrong. It's not correct. So this dot line is isothermal. And for the continuous cooling is the solid line. Okay? It's the continuous cooling. So you can find out that this transformation delayed. Okay, delayed. For example, if I drop the temperature to 550, right, and the transformation will start at this point, and for the continuous cooling rate, it will become the time with delight for transformation, right? If my cooling rate is like this. Okay, we will delay. Okay, so let's look at this, the blue line, the cooling curve, the real case, the real cooling curve. So the the pearlite structure start to form at this point. Okay, at this point. Okay. Right? And for the isothermal case, the pearlite start to form at this moment. Okay, and the pearlite completely form at this point. Okay, for continuous cooling. Okay, for continuous cooling. For isothermal cooling, the phase will completely transfer to pearlite at this point. Okay, you get what I'm saying? Okay. Let's look at this figure. What's this figure tells us? This is a TTT diagram for continuous cooling. And if there are two cooling rates, okay, two cooling rates, 1 and 2. Okay, 1 and 2. And this phase will start to transfer to pearlite start at this point, right? For cooling rate 1. And this pearlite is completely firm at this point, right? For cooling rate 1. The same that the pearlite start to form at this moment, and finish at this moment for cooling 2. Okay, for cooling 2. Okay. Okay, know what I'm saying? Therefore, for the faster cooling rate, or we say the moderately rapid cooling curve, we get the fine pearlite, right? We get a fine pearlite. I already mentioned this before. And if this cooling rate is slow, we get the coarse pearlite, right? We got a coarse pearlite. Okay. Well, maybe I would just modify this figure a little bit, because if I denote this fine pearlite here, maybe we'll disguise you to consider its Martensite structure. Okay, therefore we'll say at this point it's fine pearlite. Okay, and at this point it's coarse pearlite. Okay. Okay. Okay, so uh the continuous cooling transformation, we already know that's the real case, right? Therefore, we have to concern about the critical cooling rate. The critical cooling rate. So what's the why we have to concern the critical cooling rate? Why? For example, okay, we want to get a transformation of perlite, right? Perlite or burnite. Okay. Okay, so we need to figure out the critical rate. In this case, the critical rate is 140 Celsius per second. Okay, so if the cooling rate is faster than this one, what's gonna happen? What's gonna happen? If there's a one cooling rate, say like this curve. Okay, say it's assuming it's 200 Celsius per second. Okay, so if my cooling rate is 200 Celsius per second, what's gonna we get? What's the phase we get? What's the phase we get? So if my delta T is 250 at this temperature. Okay, 250. Just drop the temperature to 250. And with the cooling rate 200 Celsius per second, that means the perlite will never form forever and ever. Okay, you know what I'm saying? This perlite transformation will not occur. Okay, will not occur. Okay, so if the cooling rate is 200 per second, say we drop to here, what's the phase we should get? We should get. You know what I'm saying? If I drop the temperature to 250 with the cooling rates to 200 Celsius per second, and what's the phase we get? We still get the gamma phase, right? Austenite, right? You know what I'm saying? Okay, and this, therefore the cooling rate, the critical cooling rate is important to get what the phases that we want. Okay, so if my cooling rate is 150 Celsius per second, okay, we get it. Okay, so the perlite will start to form, right? The perlite will start to form. Okay, and if this cooling rate is 35 Celsius per second, it's this blue dot line, what we get. This perlite will start to form at this moment, right? This moment, right? And finish at this moment. Okay, you know what I'm saying? So during this time is the transformation, from the austenite to perlite. with continuous cooling rate, or say continuous cooling transformation. Okay. Of course, if your delta T is below this line, this yellow line, that's the starting point of the Martensite. Okay, if the delta T is the side like a 100, of course, the Martensite files will form. Okay, will form. Okay, so this shows the same idea that for the continuous cooling rate. Okay, for example, its cooling rate is very, very slow. It's 8.3 Celsius per second, right? And it'll reach the benign nose. And if this cooling rate is it's a 0.3, and during this region, within this region, the structure, if I drop to certain temperature side here, okay, if I drop to a certain temperature, and in this region is Martensite with spernite. Okay, and in this region is Martensite with ferrite and benite. Okay. Okay, therefore we can find out the if we want to get the transformation, we have to figure out the cooling rate. For sure that transformation must occur. Okay, for example, we already discussed this before, right? This critical cooling rate 140 Celsius per second. That's for sure this austenite, this pearlite transformation will occur. Right? Right. And if the cooling rate is slower than 35 Celsius, so we are getting if this slower, say this transformation rate is 30 Celsius per second. So what do we get? Right. So this curve would be like this. Right. And the transformation of pearlite will start at this moment, right, and finish at this moment. Okay. Okay, so for in this case, we see, okay, there's a curve shows that, okay, one cooling rate is 140 and the other is the 35 celsius per second. Okay, so within this range. Okay, so if we want to have the transformation, we can control the time for starting this transformation of pearlite. Again, we can control the time for the finish for this transformation of pearlite. Okay. Okay. Okay, so let's look at the this mechanical property and the ductility corresponding to the transformation temperature. Okay, that's correlated to delta T, right? That's correlated to delta T. Okay, for the Martensite structure, it has the highest the UTS, right? And then the lowest elongation, right? At lowest elongation. So this difference between them is huge. Between the UTS and the ductility or elongation is huge for Martensite. Okay. Okay. And for the Bernite structure, well, this UTS is dropped substantially, and this elongation increase. That means the ductility increase. Okay, and there's a critical point right here. Right? And with the nose of the bentonite and the pearlite at this moment, we get the peak, okay, the broad peak of UTS and the valley of the elongation, okay, of the elongation. Okay, so what's this nose? The nose is right here. I already mentioned previously. Right here, this is the nose. Okay, so it's the nose between the pearlite and the bentonite. Okay. Okay, so the finally we see the eutectoid is the TE, right? The eutectoid temperature. Okay. So for this figure, just shows the effect of the transformation temperature on the property, mechanical property of eutectoid steel. Okay, for eutectic steel. So it's the temperature T. So we have to consider is the delta T, right? Equals to eutectic temperature minus the transformation temperature. Okay, transformation temperature. So delta T is higher. That means we got the huge differences between the UTS and the elongation. Okay. All right. So let's look at some example problems of the isothermal heat treatment. Okay. For example, on the isothermal transformation diagram for in 0.45% of carbon and it's iron carbon alloy. So sketch and label the time temperature path to produce the following macrostructures. Okay, so the A, B, C, and D, there are 4 microstructures. Okay, there are 4 microstructures. 4 microstructures. So for A, it's 42%, right? This it's 42% the protectoid ferrite and the 58% of coarse pearlite, right? And the coarse pearlite. Okay, so isothermally treat at 680 Celsius from 727, right? So we get the constant temperature, okay, right? Temperature, okay, and drop the temperature to room temperature after the phase transformation is complete, okay. So O austenite transforms to pro-eutectoid alpha and the coarse pearlite at what's the starting point and the finish point for this isothermal treatment. So can you point out from this TTT diagram? So the starting point right here, right? And the finish point right here. Okay, and what's the difference between this curve, this blue curve, this curve, and this curve? What's the difference between the blue and green? What's the difference? Okay, for this line, this blue one is non-eutectoid. Okay, and for this one, this green one is eutectoid. Okay, obviously the temperature is higher than TE, right? So this is non-eutectoid reaction. Okay, and then we can use the lever rule that we already learned from the previous chapter to calculate the weight percent of each phase fraction. Okay. Okay. Sorry about that. Okay. So do you still remember what's the this phase transformation from the phase diagram? How to calculate the weight fraction? Okay. So we can look at this figure, this phase diagram. So what's the carbon content of this alloy? It's about point 45 weight percent of carbon, right? So 0.05. Wow. Somewhere right here, right? It's right here. Right? 0.05. Okay, and then we can use the lever rule to calculate the weight fraction of each phase, right? So what's the transformation temperature? 680, right? So it's about here, right here. So we can draw a timeline here, right? And we can use the Lever's rule to calculate the fraction of alpha and the perlite. Okay, alpha and the perlite. Normal sign. Therefore, the C naught is 0.45, right? So we can find the compensate the solubility limits right here. Okay, and here, right? So we can calculate, use the Lever's rule, right, to calculate the weight fraction of perlite. Okay, so what's the weight fraction of perlite? Is use this length as the denominator and this fraction as the numerator. Okay, so we can get it's about 58 weight percent of perlite. So the alpha phase is about the 42 weight percent. Okay, so we're this end our course here. Okay, so we'll see you next week.